Okay, here's number 24 from page 629. The three problems that I'm going to do are actually really good. So if you can really stay with me on a little bit on 35 and 36, I think you'll get a lot out of it. So number 24, I think we got to a good place where we decided on what we're going to compare this to, because it did say limit comparison, right, on the directions. So the decision is, what am I going to compare to? That's really the key question. And so I have to find a series that resembles this. So I do think about the limit concept here, because this n over n plus 1, as these terms continue, this is really just kind of canceling each other out. And then I have this 2 to the n minus 1. Well, you know, I have 1 over 2 to the n minus 1. That's very similar to the geometric series. And I'm going to write it like this, because maybe that's more recognizable in the form of the geometric series. So if I compare to this geometric series, r is less than 1, therefore converges. Okay, so once I have that set up, now I'm going to do the limit as n approaches infinity of b sub n, or sorry, yeah, a sub n plus 1, 2 to the n, and just a naming mechanism, over 1 over 2 to the n. And then I'm going to rewrite this to simplify the complex fraction. So I have n times 2 to the n all over n plus 1 times 2 to the n times 2 to the negative 1. And so rewriting it this way allows me to do some canceling, right? So I'm going to rewrite this one more time before I take the limit. And I'm going to have 2n in the numerator. Denominator is n plus 1. And what do I notice? The degree of the numerator is the same as the degree of the denominator. Therefore, the limit is equal to 2. And what do I know? I get a value for the limit comparison test. And that means since I get a value which is greater than 0, therefore, this original series converges. And I would say, if I wasn't directed to do so, I would say by the limit comparison test. And that's test. And that's my final statement, which kind of concludes my work. 35, however, 35 is a really good problem. Because, and this is the whole point of these last two, your options are open. So what is my thinking process? Does it look like, and I'm going to put these little notes, these are things that are going through my head. Is it a geo series or a p series? Because those are easily recognizable. Doesn't look like. No. How about, is it something that, well, I don't know that it's a telescoping series, but you're going through this flow chart of thinking. So this was a no. This is a no. So when I look at my sheet, and I just pull up my sheet, I've got the nth term test. Does the nth term test apply? Is it applicable? Nth term test says I find the limit of a sub n, and if it's not equal to 0, it diverges. Well, if I look at a sub n, the denominator is getting large, really fast. So this is going to collapse to 0. So no, the nth term test does not apply. So now I'm left with two options. the integral test. I could do the integral test, or I could do, what else could I do? Oh, I could do a comparison test. I did both of these. So I could compare, direct comparison. I could do direct comparison. I could also consider integral test. And when would I consider integral test over direct comparison? And this is, again, this is the process. I did both when I was playing with this one. The direct comparison test will work. Integral test will work. Which one is more streamlined? Which one is more efficient? Well, I'm going to choose the integral test when let me write it like this. When a sub n, which I'm looking at it in terms of f of n, is easily, I guess easily is kind of relative, easily integrable. Okay, so when I look at this function, if I were to look at this as f of x is equal to x over x squared plus 1, that quantity squared. And if I were to integrate that, I have u equals x squared plus 1, du is 2x. I think this is easily integrable. So I want to check, if I'm going to use the integral test, is this continuous? Yes. Is it positive terms? Yes. Is it decreasing? Yes. So I'm going to do the integral test. And that means what? I'm going from 1 to infinity of x over x squared plus 1 squared dx. I'm going to say u is equal to x squared plus 1. Du would be 2x dx. I don't have a 2x dx, so I'm going to manage that. So now I'm going to keep that 1/2 out. Of course, in order for me to actually evaluate this, I need to rewrite it as a limit problem. And I'm going to leave it like this. Right, so this is really, if I wanted to, off to the side, this is really u to the negative 2 du. Okay, notice I'm doing this kind of as scrap work. Right, and when I integrate this, then I'm not worrying about the limits of integration being out of sync. This is just my little scrap work. What is the integral of u to the negative 2 equal? It equals negative 1 over u. Okay, and what was u? U was x squared plus 1. So just be careful with what you're calling scrap work. This is scrap work, what I'm thinking off to the side, versus my official work. Negative 1 over x squared plus 1, and I'm doing the fundamental theorem between 1 and b. Oops. All right, so let's do the substitution. So I have negative 1 over b squared plus 1 minus, when I plug in 1, which changes to a plus, 1 over 1 squared plus 1 is 2. Okay, when I take the limit, this is getting larger, larger, larger. This collapses to 0. 1/2 times 1/2 is 1/4. Okay, so I get a value. The value, what does that signify? It means that the series that I'm finding, whether it converges or not, converges. Therefore, because the integral converged, therefore the, why is my pencil not working? Because the improper integral converged to 1/2, that means that the original series converges. Therefore, n over n squared plus 1 converges by the integral test. Yes, this is a lot of work for this one problem. Okay, 36. 36 was, let me check my notes. 36, I like 36 if you do not recognize it off the bat, and it's not easily recognizable. I do know that it is not geo-series or p-series. If I do the nth term test, I'm going to get 0. That does not apply. So could I do direct comparison, limit comparison, integral test, or is this a telescoping series? If you don't recognize that, oh, right, I could rewrite this and separate these two, or the two factors, and look at the partial fractions here that equate to 3 over n times n plus 3. I'm going to solve this. And I'm going to say, well, if n equals 0, then 3 is equal to 3a, and a is equal to 1. If I let n equal negative 3, then 3 is equal to negative 3b, so b is equal to negative 1. So now I have 1 over n minus 1 over n plus 3. Looks like a telescoping series to me. And just to be sure, let's do a few terms. 1 over 1 minus 1 over 4 plus 1 over 2 minus 1 over 5. Nothing's canceling yet. Plus 1 over 3 minus 1 over 6. Still, nothing's canceling yet. Plus 1 over 4 minus 1 over 7. Okay, things are starting to cancel. The negative 1/4 and the positive 1/4. And then what would be the next term? Plus 1 over 5 minus 1 over 8. Okay, now the fifths cancel. Plus 1 over 6 minus 1 over 9. Okay, the 1/6 canceled. So now I can see, okay, the 1/7 is going to cancel with this. And then I can now pretty much see where this is going. The 1/2, and the 1/3 will never cancel out. And they're not asking to find the sum, but if they were asking to find the sum, then I would say the sum is equal to 1 plus 1/2 plus 1/3 minus the limit as n approaches infinity of 1 over n plus 3. Okay, that's the sum. However, by telescoping definition, it converges. All right, let me look at this another way, because I think this has a good review. If I did not recognize this to be 3 over n times n plus 3, if I did not recognize this as a telescoping series, and I wanted to use the integral test, could I use the integral test? Well, it's decreasing, positive, and continuous. So I could, is it easily integrable? I've got to use partial fractions, which I've already done here. So let's just bring that back. 1 over n minus 1 over n plus 3. So let's rewrite it and pretend I don't recognize this to be a telescoping series, and I want to integrate. 1 to infinity, 1 over x minus 1 over x plus 3 dx. And they're pretty basic in terms of the antiderivative, right? It's just du over u. So I'm going to limit as b approaches infinity, 1 to b. I'm showing this work. Yes, it's an extra step, but if you're not showing it, then you're not actually applying the properties correctly. So I'm going to the antiderivative. So I have ln of x between 1 and b minus ln of, I mean, I don't have to do this separately, but x plus 3 between 1 and b. So I'm going to ln of b minus ln of 1 minus ln of b plus 3 minus the negative, so that makes plus ln 4. Okay, so I'm not going to do anything yet because I am going to combine my natural logs, knowing I can compress this before I actually find the limit. So this one minus this one means I divide ln b over b plus 3. A minus, this is really 0, so I have actually ln 4. What happens here? Right, this is, b over b plus 3. So this is really just ln of 1. Right, this is numerator, denominator, same degree. So this is ln of 1. So this actually turns out to be 0 plus ln 4. So I get ln 4 as a result, means that the integral converges, since the integral converges, I changed it to n instead of x, then converges. Okay, so that, I know that was more than what you probably wanted to see for 36, but if you did not recognize the telescoping series, then the only other option is the integral test, and then that's either one. Obviously one is a little bit more streamlined than the other. So I hope this helps. Those of you that needed to see this actually got a little bonus, and so good for you for asking those questions. I'll see you tomorrow. Thanks, guys.